Welcome to Pavebinars, webinars for the pavement community. My name is Andrew Braham, and today we're going to talk about refining particle size specifications for asphalt emulsion. Now, this is work that's been done by Mr. Pedro Diaz-Romero toward his Master's of Science here at the University of Arkansas. He obtained his Bachelor's of Science in Civil Engineering in 2020 and then his Master's in 2022. And you can find out more about Mr. Diaz-Romero in his LinkedIn profile below. When we're thinking about particle size, much of the findings have been qualitative when talking about asphalt emulsions. You see terms such as larger particle size lowers viscosity, or broad or bimodal particle size lowers viscosity, or smaller particle size increases performance and stability. But that begs the question, what is larger? What is broad? What is smaller? Can those be quantified? Now, there's two primary types of equipment to capture particle size: electric sensing zone and laser diffraction. And this work will use laser diffraction to quantify particle size. And previous research at the University of Arkansas did capture cationic slow set and cationic medium set emulsion particle size, but it was a relatively small data set. And this work looked to increase the understanding of different types of cationic asphalt emulsions. So, like I mentioned, previous research found mean values for D10 and D50. So if you recall, D10 is 10% of the particles in the particle size distribution are smaller than the D10, 90% are larger, and the D50, it's 50% are smaller, 50% are larger. But you can see here are some preliminary recommended values for the mean at D10 and D50 for CSS and CMS. And if you would like to see how these were developed, I encourage you to watch the Pavenar Developing a Particle Size Specification for Asphalt Emulsion, which was posted on September 29th, 2024. But you'll notice in that relatively small experimental matrix, there are no cationic rapid set emulsions, there are no polymer modified emulsions, and there are no performance tests in the experimental matrix. It just looked at viscosity and particle size primarily. So this work looks to address these gaps in knowledge. Let's take a look at some CRS emulsions. Let's take a look at polymer, and let's bring in a performance test. So the experimental matrix was running rotational viscometer, an oversized particle test, which is essentially the sieve test, the residue test, and then also the particle size analysis. And for rotational viscosity, we used the paddle viscometer, and for particle size analysis, we had 3 runs per replicate, so a total of 9 sets of data per emulsion. And for the performance test, because these are CRS emulsions, that's a rapid set emulsions, we used the sweep test. And we ran 3 replicates on the emulsions that we tested. And the 3 emulsions were a CRS2, which is a high viscosity asphalt emulsion, a CRS2L, which is a high viscosity latex polymer, and a CRS2P, which is a solid polymer high viscosity. And these are all cationic rapid set asphalt emulsions, CRS. We tested materials at 2 days, 5 days, 7 days, 14 days, and 21 days, and then every 21 days until 180 days. So about once a month in between day 21 and day 180. As I mentioned, we used a laser diffraction particle size analyzer, a Horiba LA350AP, and we performed the ASTM D7000 sweep test, which is called the standard test method for sweep test of emulsified asphalt surface treatment samples, and it's recommended in NCHRP report 680. And like all NCHRP reports, all you need to do is search online the term NCHRP report 680, and you are able to download it for free. And as I mentioned, what we're looking to do here is fill some gaps on preliminary research that we did with CSS and CMS emulsions and expand it to CRS emulsions. Now, Mr. Diaz-Romero did a very nice job of presenting this data, and this is kind of the template that he used to show all this different data. So you can see here we have all CRS emulsions at day 1, day 25, and day 180. On the y-axis is the percent volume of the particles. On the x-axis is the particle size. And you can see under each curve are 3 vertical lines, and each of those lines corresponds to D10, D50, and D90. So on the far left vertical line for each curve is the D10. That means that 10% of the volume is smaller, or 10% is contained, and 90% is larger. D50 has 50 on each side, and then D90, 90% of the volume is to the left. It's smaller than the D90 particle size, and 10% is larger. And you can also see here that the maximum size of particles for CRS-2 is approximately 20 microns. But it's also very clear to see that as time progresses, as the emulsion stays in storage, lower and wider curves begin to occur. So the day 1 is that top upper left-hand solid dashed line. Day 25 is the solid line that's in the middle, down and to the right a little bit. And then day 180 is even further down with the dots in the dashed line, and that's at D180. So not only is your particle size increasing, but the distribution, the span, is also increasing. So lower, wider curves over time, and they're shifted to the right. Now, unfortunately, or because it's research, this is what it is, but we did not see the same trend for CRS-2L. So this is the latex modified CRS emulsion. And you can see here day 1, day 62, and day 180. It is true the curves do shift to the right, but it is not consistent that they're lower, because actually D62 had the lowest curve. And then it was day 180, and then day 1 had the highest curve. And they don't look like they're really getting much wider either. The width tends to stay the same, but it tends to move to the right. So some different things going on here, but still of interest. And another thing of interest is the maximum particle size was approximately 25 microns for the -2L. Now for the CRS-2P, again, a different material and a different set of data. Here, the graphs are very similar. One could argue that maybe they shift up and to the right just a small amount, but this is just the average plots, and I would assume that that's within the deviation. So really, at the end of the day, the curves are pretty similar here between day 1, day 67, and day 189. Now, one thing that is of very interest, though, is how much larger the particles are, especially anything above that D90. You're getting up to almost 100 microns in size, and this is with the CRS-2P emulsion. So very interesting to see the differences between a CRS-2, a CRS-2L, and a CRS-2P. Now, another thing that Pedro did was he attempted to, again, get some preliminary specifications. So what we did is we also measured the viscosity at each one of these time periods. So we have up to 180 days of storage time, and you can see the viscosity is increasing. It's not a tremendously strong trend, but it is going up. And what we did is at 800 centipoise, which is the maximum value, we found a storage time of 25 days for the CRS-2. And so what we did is we plotted a similar graph to this for the CRS-2L and the CRS-2P. And basically the premise was, at what storage time did 800 centipoise viscosity, the maximum in the spec, occur for each of these 3 materials? So for CRS-2, this was about 25 days. Now here, CRS-2 is the graph on the bottom. It is the orange squares, and you can see the storage time is on the y-axis, on the x-axis. So we took 25 days and we went up to the regression line for CRS-2, and then went over to the left to find the median particle size, which looks like is about 1.7. Now, we have constructed similar curves of viscosity versus storage time for CRS-2L and CRS-2P, and you can see CRS-2L had a storage time of approximately 61 days, which is where the 800 centipoise occurred, and that's a median particle size is about 3. CRS2P was about 65, 67 days, and that goes all the way up to a median particle size of about 7.7. So again, for each of these 3 emulsions, we found what storage time corresponded to an 800 centipoise viscosity, and then we found the corresponding median particle size, and this is based on regression lines of all of the data. And this is what we found overall for all of the values. The previous graph had the median, so for CRS-2 is 1.7, but we found it for the mean, the mode, the D10, D50, D90, the span, which is D90 minus D10 divided by D50. And then also we ran the sweep test at the 25.3 days, and we found out the percent material retained. And so we did this for the CRS2, we did it for the CRS-2L and the CRS-2P, and we were able to come up with these recommended performance and particle sizes, again based on viscosity, but now including not only emulsion properties, but also a sweep test as well. So in conclusion, 3 CRS emulsions were tested, a CRS-2, a CRS-2L, and a CRS-2P. And we focused on the D50 and the sweep test. We found the storage time at the maximum viscosity, 800 centipoise. We found the corresponding particle size at that storage time, and we found the sweep test values. And what we're able to do is find a suite of numbers for a potential specification for particle size. So for D50, CRS-2 is 1.9 microns. For the latex, it is 3 microns. And for the 2P, the polymer, the solid polymer, is 10.7 microns. And for the sweep test, we found corresponding values for that too. So this is moving from not only a particle size to also potentially a performance specification. Now, I do want to reiterate that this is a relatively small data set. Again, only one type of emulsifier, one type of asphalt binder, but we did look at 3 different types of CRS with and without polymer or latex modification. Now, just like Logan found out in previous particle size research, how many number of particles and the volume of particles is very important. Also, how we prepare the samples for particle size is absolutely critical. If you've ever run a particle size test, you need to dilute the material, which literally means you're taking 1 or 2 drops of asphalt emulsion, putting it in a dilution liquid, and then running the particle size. So it's taking 1 to 2 drops and assuming that that is the representative of the entire sample. That's a pretty big assumption. So how we prepare for the particle size is absolutely critical. And one of Pedro's big takeaways from his research was listing all of the different things that could potentially be changed during sample preparation and recommending that we look into more of that and more research was needed. So I just covered the highlights from this paper. Here is a full citation, and also there's the DOI link. The DOI link can be found in the description below as well. But again, thank you very much for joining me today, and I hope you have a wonderful day.